Okay. Well, thank you, everyone, for joining our remote meeting this morning. This is the second seminar the New York State Center for Clean Water Technology has offered. And we will be doing these on a monthly basis, the first Monday of every month. Last May's presentation, Chris Gobler, our director, gave a broad overview of the center's activities and what the center is doing to solve contamination of water problems on Long Island. And that includes drinking water as well as wastewater. Today, Caitlin Asato, my colleague, and I will be talking about optimizing the design of NRBs. That is, their non-proprietary nitrogen removing biofilters. And they're particularly effective at removing nitrogen, and they remove some organic contaminants as well. So on the agenda for today, we'll first just go over a bit of basic chemistry so that you understand the principles in back of our designs. Then we're going to go over 3.5 years of testing at the Massachusetts Alternative Septic System Test Center. That center uses the same wastewater for all designs there. So it's an excellent place to make comparative, to do comparative analysis between different systems. Then Caitlin will talk about residential installations in the actual real world and with very variable wastewater influent. I'll come back and talk about some of our efforts for wood chip box polishing units. We'll then summarize our findings and talk about future research. But lastly, we want to get to what all of this means in terms of impacts on Long Island water, including drinking water and groundwater and marine ecosystems. So far before man invented cesspools, even about hundreds of millions of years before man invented cesspools, there was a nitrogen cycle on the earth. And nitrogen cycles between non-reactive forms, or one non-reactive form, which is nitrogen in the air, and that's about 78% of the air around us, and reactive forms, such as organic nitrogen and ammonia or nitrate. So in the natural world, there are microorganisms in the ocean and in the soil which fix air, nitrogen air, into organic nitrogen, which easily becomes ammonia. And then there are other microbes which oxidize those forms of nitrogen into nitrate. And then other microorganisms which denitrify nitrate back into the air. So it's a complete cycle. And until 1910, that cycle was in balance until man figured out how to industrially fix nitrogen. And that, of course, has led to many of the problems that Chris addressed last week in terms of excess nitrogen and creating problems for especially aquatic ecosystems. So fixation occurs by microbes in the soil and the ocean. And then on the continental shelves, nitrate down here is denitrified back into air, especially in soils and continental shelves. Now, this is the exact process that our systems do. We basically don't store nitrogen. We remove it from wastewater over here as ammonia or organic nitrogen into nitrate and then back into air. So this diagram is a fairly simplified version. There's a number of steps from nitrate to nitrite for it to be properly denitrified. And one of those steps can produce nitrous oxide, which is a greenhouse gas. And our center very much doesn't want to produce systems that would do that. And that's something that we are monitoring. We don't believe that it does that, and I'll get to that point further in a minute. In terms of the way our systems work, there's a septic tank that's pumped to a distribution field that overlies 18 inches of sand, that overlies 18 inches of sand and wood chips. So there's a coupled nitrification, denitrification, just like in that chart of the natural world I showed you. Now, because sites are different, they're not all the same, we have promoted 3 different configurations of this basic coupled nitrification, denitrification design. One is a line system, an unlined system, and one has a wood chip box off to the side. We have one of each of these designs at up in near Otis Air Force Base at the Massachusetts Alternate Septic System Test Center. We've had that up there for 3.5 years. And in the last, over the course of the last 2 years, we've installed experimental phase designs, 8 of them in Suffolk County. So the way these systems work, the question I brought up earlier, most of the industry looks at just removal of nitrate, which you can see down here on the x-axis. This is consumption of nitrate. And as nitrate is consumed, then N2 is produced. And if this particular set of data shows that for every milligram of nitrate consumed, 0.82 milligrams of dinitrogen, or nitrogen that's in the air, are produced. So it's not quite a 1-for-1. That's because in this lab-based experiment, there's some unsteady state conditions. So some microbes are consuming some of that nitrate. As well, there's a bit of error. I've run quite a few of these analyses, and typically we see from about 0.8 to about 0.95. So very little room for any intermediate products like greenhouse gases. We've also monitored these systems out in the field, and so far see no evidence that there's any production or generation of nitrous oxide from these systems beyond what you might expect from a wastewater treatment plant, which is very small, on the order of 2% or less. And so far, it's hard to prove a negative that it would never happen, but we've seen very little evidence of it. So I'd like to discuss the specific 3 configurations. This is a lined NRB design. So there's a topsoil, then 18 inches of sand. This chart is in centimeters, but that's 18 inches of sand, and then 18 inches of sand and wood chips. This unlined system is a system where there's final deposition to groundwater. In other words, we don't capture the effluent from this. It goes directly into the environment. So Suffolk County, and as any regulator would, requires that there's some soil underneath systems, and for drain fields, they require 2 feet of soil. So if we have about a 1.5 feet of topsoil, 1.5 feet of sand, and 1.5 feet of sand and wood chips, that's about 4.5. Let's err on the side of caution, call it 5 feet. And then we need 2 feet above any potential groundwater. So these systems would work with depth to groundwater of 6.5 to 7 or above. They would be fine. The lined system is like the unlined system, except in 2 ways. One, it has a liner, as you might expect, and And also what's not shown on the diagram is there's a pipe that captures all of the effluent that comes out of the system and takes it up to the interface between the sand layer and the sand and wood chip layer. So this layer is always saturated because there's a hydraulic head created by this pipe going up here. And then that pipe goes to final disposal. So in terms of depth requirements for these systems, you've got, call it conservatively 3 foot of topsoil and sand, and then you have your pipe, and that has to go on a gradient down to final disposal, which can be either a leaching galley or a concentric leaching pool. And if those are, depending on the space in the site, you could use a 4-foot galley, and underneath that, you need 3 feet before you get to groundwater, so that would be 10 foot. Or if you had the space, you could use 2-foot galleys, and then you would only need 8-foot depth to groundwater. The wood chip box variation is very interesting. We wanted, because the wood chip box is a lot smaller, a lot less volume than the layered systems. So for instance, it's about 1/4 of the volume of the layered systems. And we wanted to see if that smaller volume could continue to, or could denitrify the nitrate coming out of the sand layer here. It goes from here, goes from the sand layer here, down into deposition here, and then into the wood chip box, which is in here. Turns out it denitrifies very, very well, even though it's a very small volume compared to the layer cakes. And I'll talk about that research that we're doing into using those with IA systems in just a moment. So 3.5 years of testing NRB designs at MASDIC. What I'd like to, that has involved a lot of research and a lot of monitoring, and I'll talk about 3 different parts of that today. I thought we could talk just about that for the entire hour. So we did a tracer experiment to find out the residence time of the sand bed, that is how long the wastewater stays in the sand bed, and how long it stays in the unlined system, in the unlined biofilter. We've done experiments to optimize the size, the footprint of these NRBs. We did that by increasing loading rates. I'll also talk about spatial analysis, or monitoring the changes in nitrogen with depth, and then talk about the seasonality of these systems. So it's a really straightforward matter to calculate the residence time of water in a tank or in a lined NRB, say. It's just whatever goes in, you take, and what comes out, you take the volume of the system and you divide it by the loading rate to get the number of days that any parcel of water would stay in that box. But if you don't have a defined system, as in the case of an unlined system, then you can't do that, what's called an HRT calculation. So what we did was we put a bunch of bromide in the pump chamber upstream of the unlined system at MASDIC. Sodium bromide is inert. It won't affect the operations of the system. And then we measured the bromide that came out in a lysimeter, a pan lysimeter that was underneath the sand bed, and then another one that was underneath the denitrification layer. And what we found out was that it takes about 1.6 days that the water spends in that unlined sand bed, and another 3 days in the biofilter, in the denitrification biofilter of the unlined system. That's a little bit less than the in the theoretical calculation that we did for the lined system. But those numbers are fairly close considering the era involved in this experiment and trying to capture the percolate in a pan lysimeter. So they're pretty close. The real difference here is with the wood chip. As I mentioned before, it's much smaller, so the water stays in there for less. That doesn't seem to have affected its performance, though, as I'll discuss just momentarily. So the experiment to increase loading rates, we wanted to push the boundaries of the systems to see how high we could load them, because of course in any county there's going to be regulators, and they rightly so set what's called a design flow. So any septic system has to meet a certain gallons per day capacity. So you can do that either by making a bigger system to handle the flow, or loading the flow in a smaller system faster. So what we wanted to do in this experiment was find out if we kept loading it at a higher rate, when would that either fail because the loading was too high, and when it did, what was the nitrogen level at that rate? So that would get us to what is the optimal size system, the smallest system we could design, in other words, and still stay, very importantly, within our center's guideline of 10 milligrams per liter of nitrogen or less. I'm sure last presentation, Chris went over our 10-10-30 rule. And so everything I talk about today, all our systems, they're designed to get under 10 milligrams per liter of nitrogen or less. So the systems at Mastic are 12 by 28. So that's a 336 square foot system. We started loading that at 220 gallons per day. That works out, if you normalize the gallons per day to the square foot, you get of the system, the 336, you get 0.65 gallons per square foot per day. Well, Suffolk County, for a 4-bedroom house, their requirement is 440. So for 440 at this 0.65 gallons per day loading rate, you'd have to build a system that's 677 square feet. And our early installations in Suffolk County used 0.75 gallons per square foot per day, so very close to that. But we wanted to see, could we go load greater than that? And we want to do this, of course, over a long period of time, not for a couple of weeks. So, and especially including the winter, which is, as I'll discuss soon, the really difficult period for denitrification. So we wanted to run it over the winter. So each time we ran it for over 18 months. So what we found out at 330 gallons per day, or roughly 1 gallon per square foot per day, then you can build a 446 square foot system if you want to hit Suffolk County's 440 regulatory design flow. Our systems could do that for the line system and the wood chip box. We got basically 8 milligrams of liter running not just at the lower rate, but at 1 gallon per square foot per day. For the unlined system, its performance was above 10 milligrams. So what we're recommending to engineers and regulators based on these experiments is that for line systems and wood chip systems, you size the system, design it based on 1 gallon per square foot per day. If it's an unlined system, you design it based on 0.75, which is the rate that we used in our early systems, which, as Caitlin will tell you in a minute, our experimental systems in Suffolk are working very well at 0.75 gallons per day. When you try and load these systems, these drain fields, at above 1.3 square foot per day, you get a, you reach the hydraulic capacity of these systems, and you begin to get pounding of water. So we don't want to do that. So there should be a big X here. None of our systems are we recommending to go above 1 gallon per square foot per day with the current design configurations we have. This is the, if you look spatially at what happens in the system. So this is the amount of total nitrogen in the system in milligrams per liter. And in the influent up at Mastic, it's 43 milligrams per liter. Just percolating down through the sand filter, this is nitrified percolate. So this is captured in a lysimeter at the bottom of the sand bed. It removes on average about 1/3 of the total nitrogen. We think that's because there are anoxic microzones in that otherwise oxic layer. And if there's a lack of oxygen around, many facultative microbes will use the oxygen that's attached to nitrogen in nitrate for their oxygen source. They'll prefer to use oxygen directly, but they won't go too far to get it if there's a biofilm or an anoxic microzone. So we think that's what's going on here. The other interesting point about this spatial analysis is that these systems denitrify, nitrify really well. You can see all of it is in reduced forms, TKN or ammonia or organic nitrogen here, and it's all converted, almost all converted in the sand layer to nitrate. And then in the final effluent, it stays in the form of nitrate. Now, the residual amounts, this is the long-term average for both performance periods over basically the 3.5 years. The dominant form left is nitrate. And the reason is there's some nitrate collected in the winter in these systems. So here's the seasonality of the lined and wood chip box. The unlined system would look exactly the same. Don't happen to have it up here. Here's the line, here's the wood chip box. The blue is temperature. So you can see this is winter time when the temperature goes down, summertime when it goes up, winter time when it goes down, and so forth. And this orange line is nitrate, and the small gray data is TKN. So the system is almost all nitrified. It's all nitrified. It's all in nitrate up here. But in the wintertime, when the temperature is low, the amount of nitrate goes up. So denitrification attenuates. So if you want to build a more efficient system, the thing to do is to focus on how to reduce nitrate in the winter. Maybe how to provide more electron acceptors in the winter. And that is one of the things that the center is focused on currently. So with that, I'm going to turn the computer over to my colleague, Caitlin Asato, who has joined us and who has studiously been keeping a 6-foot difference from me. And she'll be here and I'll go away and then I'll be back.
Okay, thank you, Stuart. Following the success of the systems installed at Mastic, the center continued to install nitrogen removing biofilters at various sites around Suffolk County. So these are mostly at locations owned by the Suffolk County Department of Parks, along with 2 online systems installed at the Nature Conservancy location at Uplands Farm Sanctuary. And all of these have been online anywhere from just a couple of months to 2 years. So these were installed under experimental approval through Suffolk County's Article 19, which requires between 2 and 5 systems to achieve 75% of systems with effluent less than or equal to 19 milligrams per liter over 12 consecutive months. So once that is completed, and we expect the lined and unlined systems to meet that requirement within the next year, and the wood chip box systems shortly after, then we would qualify for pilot approval. So if we have 2 or 3 systems already installed under the experimental phase, we can install between 5 and 6 additional ones to qualify for piloting. So from there, we would need to meet similar requirements over a 12-month monitoring period. From there, we would qualify for provisional approval, where we would need at least 20 units installed. And the final goal there would be to get to general use approval, where they could be installed anywhere in Suffolk County with continued monitoring. So this is a summary of the design flows of each of the NRBs installed in Suffolk County. As you can see, they are designed with flow rates well within where we would expect, well below where we would expect hydraulic failures based on our experiences at MASDIC. So they are fairly large in footprint right now, but we can be pretty confident that they will all perform. And as you can see from the rightmost column, the couple of sites where we do have flow meters installed, the actual flows are far below the design flows, which is what they're for. So that's good. This chart shows summaries of performance of all of our NRBs over the entire monitoring period. So anywhere from a couple of months to 2 years. For each system, we have the influent on the left and the effluent on the right. And a couple of things might catch your eye about this slide. For one, the influent qualities can vary quite a bit from house to house. For example, Uplands Farm 2 has not had residents for about a year, so the quality of the septic tank effluent is a little bit different. Another one that might catch your eye is Prosser Pines 1, where the effluent quality is much higher than the other ones. So you'll notice that that one also has higher effluent quality, but on a percentage basis, it's not quite so bad. So this red line here is the 19 milligram per liter standard, and all of our systems except for Prosser Pines 1 are meeting that standard. And this blue line is the 10 milligram per liter standard that the center sets internally, and all except for 2 of our systems are currently meeting that. However, on average, they're all, if we look at the average by the system type, they're all below 10. And this chart shows a replication of one of the analyses that Stuart presented on our MASDIC data. So on the left, we're looking at the water quality at the interface between the sand layer and the wood chip layer. One thing you might notice right away is that there's a lot of variation between our sites, even between the ones that are the same configuration. However, we do see that, like at MASDIC, there is a substantial amount of nitrogen removed just within the sand layer. However, it is a lot more than MASDIC, where we had about a quarter to a third of nitrogen removal. In Suffolk County, we have over 50%. And then if we look at the right side of the graph at the final effluent coming out of the NRBs, whereas at MASDIC, most of the remaining total nitrogen in the effluent was in the form of nitrate and nitrite, so the blue section. In Suffolk County, most of our systems are producing more TKN in the effluent. So in summary, most of our NRB installations in Suffolk County still achieve less than 10 milligrams per liter in effluent, even though the influent nitrogen was higher in most cases than at MASDIC. All NRBs showed a lot of nitrogen removal in just the sand layer, although the ones in Suffolk County showed a lot more. All NRBs show less nitrogen removal in cold temperatures, and the final effluent at MASDIC, most of the residual nitrogen was in the form of nitrate, and in Suffolk County, it was mostly in the form of TKN. So with that, I'll ask Stuart to come back and present on our work with wood chip boxes.
Well, thank you. Trying to keep 6-foot distance. So I said earlier in the presentation that I would talk about wood chip boxes a bit more and their use as polishing units for IA systems. So Suffolk County DHS actually asked us to look at this area of research because these wood chip boxes are small relative to general footprints for drain fields. And the conclusions that we could draw here would be different than the conclusions about hydraulic capacity or nitrogen removal performance in the NRBs that we talked about earlier. And the reason is here, as a polishing unit, these systems would be used for final effluent. So final effluent is already treated. So it won't have all the organic matter or the potential to build up biofilms, which what regular NRB treating wastewater would have. Also, these systems are smaller, so there were several questions. At a high loading rate, 3 gallons per square foot per day, what's the smallest system that we could build? That was one question. Another was, what would be the maximum loading rate for a drain field that looked like one of our NRBs with a sand and wood chip, one of our layered NRBs, which have a sand and wood chip mix at the bottom. To answer these questions also involves looking at the optimal size and type of wood chip to use. So we've done in our research trailer some work on some of these questions, and we'll do further work on others. So to the right here is a screening process. This is how we determine the optimal size of our wood chips. So we're in the process of those experiments now. And then for determining the size of the wood chip box itself, what we did was we constructed barrels with different volumes of wood chips. That would give you, so the larger the volume of wood chip, the larger the hydraulic retention time, the longer the water would stay in that bigger volume of, or bigger volume of wood chips. The barrels are all the same size. And this is a medium-sized volume of wood chips and a lower volume of wood chips. Well, what we found out in monitoring this since last summer is that as long as you have a residence time of 1 day, that's enough for denitrification. You can load it at 3 gallons per square foot per day. You can have a very small system, but if it's small enough to allow the residence time to go under a day, then almost immediately you compromise the removal or the denitrification, the removal of nitrate. So we're continuing to monitor this to see if there's any changes over time. So far, oak and pine seem to perform about the same, but we're continuing to consider this question of wood chip types as well as wood chip sizes. So our key research findings: NRBs remove nitrogen to N2 gas. We haven't found evidence yet of a lot of intermediate production of potential greenhouse gases. Footprints for lined and wood chip box systems, we have 1.5 years worth of evidence that you can load them at 1 gallon per square foot per day and achieve under 10 milligrams of nitrogen per liter in final effluent, 8 actually. For the unlined systems, you have to build them larger because you need to load them at a lower loading rate, so 0.75 gallons per square foot per day to get, again, 8, but at least under 10 milligrams per liter. With the current layered designs, they reach hydraulic capacity at more than 1 gallon per square foot per day. We get significant end removal, total end removal in sand beds, about 1/3. And the key to improving these, to optimizing these systems further is to design them so they perform in cold temperatures better than they do presently. And that's a challenge we're working on. And denitrification in wood chip boxes is works at high loading rates as long as you keep under 1 day residence time. We are still working on using a drain field for a polishing unit. That's awaiting an installation at our research trailer. So questions for further research, how to overcome hydraulic limitations of the drain fields so that we could increase flow beyond 1 gallon per square foot per day and decrease system foot size. How to increase denitrification at cold temperatures. And we're looking at many different solutions for this. Wood chips for either boxes or drain fields, size and type, and we want to get more installations in the ground. We're also looking for ways to improve the resiliency and reliability of these systems. Although, so far, they've been very reliable in our in-ground systems in Massachusetts and in Suffolk County. So, what does the technology mean for the environment here on Long Island? Let's just go through a real simple calculation. We know that households produce, a 4-bedroom household on average might produce just under 300 gallons per day. And we also know from research literature that wastewater has on average about 60 milligrams of nitrogen per liter in it. If we take that, multiply it by 520,000 unsewered homes on Long Island, you get a lot of nitrogen percolating into groundwater, about 14,000 tons of it every year. And if you use conventional ratios to account for some removal in the vadose zone or in aquifers, then that ratio would be about 0.5, so you get about 7,000 tons. And that's very conservative for Long Island because there's a lot of houses that are very close to the water, and therefore the effluent doesn't spend much time in the vadose zone or in aquifers. It goes pretty directly within within a year or so out into the ocean. So that means for 1 milligram of nitrogen reduction, if you can reduce it by 1 milligram, that's going to save you in nitrogen loading to the marine systems 116 tons of nitrogen per year for these houses. So if you took, for instance, the 8 milligrams that we're getting in our systems that we proved we can get in Suffolk and at Mastic, you can get rid every year of close to 1,000 tons of nitrogen entering the marine systems, 950, based on these assumptions. So we'd like to acknowledge people who have made this research possible. And Governor Cuomo started our center, so we are very indebted to him for to be able to do this work, as well as County Executive Steve Ballone. They've just put together a super great program here to confront the cesspool crisis on Long Island. And Peter Scully, who makes this happen in Suffolk County. Steve Engelbright and County Legislator Kara Hahn have been enormously helpful to the center in helping us to obtain financing. The folks at DHS, at Department of Health Services, Justin Jobin, Julia Priello, and John Songen are great collaborators. And also Susan Van Patten and Kun Tang at the New York State DEC in the Water Department. George Heufelder at MASDIC. I can't tell you how much I have learned from George in the last 4 years of working with him and how enjoyable that's been, as well as Dave Potts at Geomatrix and George Loomis at URI. So our thanks go out to all of them. And with that, I think we're going to take questions.
Stuart, I have a question.
Yes.
So you mentioned in your presentation first that all of the systems nitrified well at all temperatures, and you mentioned a few times that you noticed denitrification attenuate at colder temperatures. And you also mentioned that you have several things that you're doing in order to improve denitrification at colder temperatures. Can you, one, tell me why denitrification attenuates at cold temperatures? And two, can you tell me what you're planning to do to improve denitrification at cold temperatures?
Sure, great question. So one thing that I've noticed at MASDIC, after staring at the data for maybe a bit too long, but because it is kind of messy data, but it seems that certainly it's very clear denitrification attenuates at cold temperatures, but the nitrogen removal in the sand layer doesn't seem to. So if that's being denitrified in anoxic microzones, it's because it's using carbon that is in wastewater. There aren't any wood chips up in the nitrification layer. So that's a hypothesis. I haven't proved it, but if it was carbon that was in wastewater, then it's more labile. If the carbon is being supplied by the wood, you first have to rely on cellulolytic bacteria to break up the wood to allow the hydrolysis of carbon, to allow that carbon to be bioavailable to the denitrifiers that need it to convert nitrate. So maybe instead of it being a general control on the cold temperatures being a general control on nitrifiers, maybe it's really on these cellulolytic bacteria that they don't produce as much carbon at colder temperatures. If that were true, then the question is, okay, well, carbon is supplying an electron donor in this process, in the chemical reaction. So how do you supply an electron donor? So that gets to the second part of your question. And so we're looking at ways to supply electron donors, whether that would be materials or even electrochemistry may have some applications here. This is all on the drawing in the early stages right now, but interesting research. So thank you for that question. Are there others?
Sure, we have a couple
Okay.
Can you give more information about wood chip sizes?
So question about wood chip sizes. Still a work in progress. What we've found so far, there's a couple things with wood chips. One, you don't want dirty wood chips. You don't want leaves. So really you want the wood chip processor who's chipping the wood to either be taking all the little branches and leaves off or to do it in the winter time. And then in terms of sizes, we've been using screens. So the installations that we've done so far, we've gone to Home Depot and we've used a quarter of an inch, screens. That seems to get rid of all the dirt and you get a nice size looking wood chip. That was that picture on the right. I didn't show a picture underneath it, of what you don't use, but that's mostly small particles. But we're still researching this question. So we may screen at 1/8 of an inch in the next experiment. There's another question?
Any idea of cost versus proprietary systems?
So our first installations were very expensive. There's a huge learning curve in any design. Probably the first iPhones were pretty expensive and the first calculators were pretty expensive. So there's a real learning curve here. As we enter the pilot phase, and as Caitlin explained earlier, we're right at the precipice of doing so, and we have funding for quite a few installs. Our number one priority will be to reduce the cost of these installations so they are competitive with at market prices with IA systems, with commercial IA systems.
Can you explain more about what types of wood chips are used, the preferred size, and why is pine and oak being used? How long do they expect to last? Do they break down over time?
Sure. Okay. So a couple of questions there. So let me ask them one at a time, answer them one at a time. First, in terms of carbon longevity. So the answer to that is that no one knows 100% for sure, but we can look at some guidance points. So during Sandy, this giant oak in our backyard fell over, and I had to pay somebody to come and chop it up, but I didn't want to pay somebody to grind the stump. So that stump is there, and it doesn't look very much different now than it did in 2012 after Sandy. The other end members are, so one end member to consider would be a tree that falls in the wood. And, it's going to take 10 years or more for that to decay, but the carbon is still going to be in the soil. So even way more than 10 years. And that's in a fully oxic environment with lots of animals and insects breaking that wood apart. The other side of the equation might be a Viking ship. So there was one I visited in Stockholm, and a Viking king built this ship, and they launched it in Stockholm Harbor, and it sank. And after World War II, they dug it up, excavated it, and brought it up to a museum that I visited. And all of the timber is still really intact. That's because it was in an anoxic environment where there weren't a lot of bugs or microbes to break down that wood. So it breaks down very, very slowly. So in terms of carbon longevity, maybe those are the endpoints. Maybe the best, longest record is up at Waterloo. Robertson et al. Published a paper in '95 where they put in a similar wood chip biofilter that was receiving septic effluent. And in 15 years later, they published a paper, and it was still denitrifying, and that was in 2010. And now they're still going, and it's still denitrifying. So that's 25 years already, and it's still going strong. The other question was on wood chip type. Why did we choose pine or oak? That's mostly what's on Long Island. But it's an interesting question as to whether maple or something else would work better. So far, we haven't found any differences at all. Other question?
Yeah, how often do the wood chips have to be refreshed or replaced?
So that's kind of the question I was just addressing, and I think, you know, the answer from Waterloo University in Canada again is at least 25 years, but probably much longer. If our wood chip box allows access to do that, or there to be a reason to do that. Next question. Okay, so those were all the questions in the chat. Are there any more questions from anyone on the line who wants to ask verbally? If not, I think that's the end of the presentation, and I thank you very much all for attending.